Okay, let's do some physics. So I'm starting with number 5, and I will work my way through the rest of these problems. And I'm not sure yet. I may split them into multiple videos, but let's just get started with number 5. So 5 asks us about the skier going up this hill. Okay, and this is one of, if not the most complicated problems. There's just a lot of pieces. They're all pieces that we've done before, but just put together at the same time. So we learned that this skier has an initial speed of 12 meters per second, goes up to 2.5 meters. There's an angle to the hill. There's a coefficient of friction between the skis and the snow. And we want to know how fast the skier will be going when they get to the top of the hill. A good question, but a tough question. So how do we get started? Well, I'm going to try to get started with a chart. So just a reminder, there's a 35-degree angle here. This height is 2.5 meters from his current height, the skier's current height, to the skier's final height. This will be the skier's final position here and their initial position down here. Let's start with some bar charts, energy bar charts. So at the beginning, the skier has kinetic energy. If we call this a height of 0, then that means that the skier has no potential energy currently, so only kinetic. And that's nice if we can boil it down to just one kind of energy at the beginning. So initially, they have kinetic energy. How much? 1/2 mv squared. We know the mass, 60. The velocity, I believe, is 12. Let me double check that. Yep. And so, I think this is going to be 4,320. Yep. So in terms of just how much energy does the skier have right now, 4,320 joules. Well, then what happens? Point number 2, kinetic energy, potential energy. We know that the skier has some potential energy, and we even know how much potential energy the skier has. That's going to be mgh. So 60 times 9.8, and their height now is 2.5 meters. So 60 is 2.5, whoops. That is 1,470 joules. Okay. So if the skier did not lose any energy, and there should be more energy over here at the beginning. If there was not any energy lost from the system, and the system I just mean the skier, and technically Earth too, but just the skier, if he or she didn't lose any energy, then they would have 4,320 minus 1,470, whatever's left over would all be kinetic. But we know that some of the energy in the system was lost because friction did some work. Okay? Friction removed some energy from the system. And we want to know how much. Well, what is the work of friction? It is the force that's doing the work, friction, times the displacement, or the distance over which it does the work. So what is that distance? Well, the skier goes all the way up this hill. And if you'll notice, I've kind of got a nice little triangle now, where the hypotenuse is the distance up this slope. The height of this is not great. The height of the triangle is that 2.5, and I can find the displacement, which would be the length of the hill as the skier goes up to the top. So let me write the equation out. 4,320 joules of energy at the beginning, minus some work done by friction. So friction is going to take some of that energy out. Is going to be equal to the kinetic energy at the end, which we don't currently know. We just know that it's 1/2 of the mass, which is 60, times the final velocity squared, plus 1470. So I'm going to put that number and this number together. 4,320 minus 1470, 2850, minus, what is work? It's the force of friction times the distance. And I'm going to find that distance right now. 1/2 of 60 is 30. So what is this distance? Well, I know the angle is 35 degrees. And I know that sine of an angle is equal to the length of the opposite side over the length of the hypotenuse. So in this case, sine of 35 is equal to the opposite side. So opposite from the angle is the 2.5 meters over the hypotenuse, which is the distance traveled. And so we got to solve that. That is 2.5 divided by the sine of 35 degrees. And you get 4.36 meters. That is the distance that goes right here. And notice it's not the height of the hill, or the height that the skier gains. Now the skier is 2.5 meters of elevation above the earth, higher than they were before. It's the distance that the skier goes through the snow. Okay, so friction is acting at every moment as the skier goes up the hill. So because the hill is 4.36 meters long, that is the distance over which the work of friction is done. Okay, so now you notice we've got this equation right here, and it has two unknowns in it, the force of friction and the velocity final. It asks us for the velocity final, so maybe there's a way we can figure out the force of friction. The force of friction, as we've studied before, is a coefficient of friction times the normal force. The coefficient of friction they gave us, 0.08, times the normal force. Okay, well, what is the normal force? It's not just his weight, because he's not on the flat ground. He's on a slope during that time. So here is my skier now. He's a box. Gravity points this way. The normal force is perpendicular to the surface, so straight up. And because the skier is going up the hill, friction is acting against that, pointing down the hill. And that's why it does negative work, because it opposes, it's in the opposite direction of the displacement up the hill. Okay, so we need the normal force, because that's what will help us find the force of friction. So how can we find the normal force? Newton's first law. Adding up all the forces in the y direction should give us 0 because there's no acceleration. So we've got the normal force pointing in the positive direction minus, not the whole force of gravity, the force of gravity times the cosine of theta. So the normal force is mg, that's what the force of gravity is, 60 times 9.8 times the cosine of 35. Normal force is 481.7 newtons. Okay, and that is not what we plug in here. That's the normal force. We want the force of friction. So we just do force of friction is 0.08 times that normal force we just got, 481.7. 38.5 newtons. Okay, so initially we had 4,320 joules of energy. Think of that like an allowance, and how do we spend it? 1470 was spent on potential energy, gaining us some height. some of that energy was used to overcome friction. So I'm going to multiply that by the 4.36. 168 of those, that's what this number is, 167.95. All right, so once we were done with potential energy, we had 2850 left in our allowance. Friction takes another 167.95 of that. All right, so there are 2,682 joules of kinetic energy when the skier reaches the top of the hill. So they still have quite a bit. A little over half of their energy is still kinetic. So we divide by 30, that was the half of 60, and then we take the square root and we'll find the final velocity. So a skier that was going, they were going 12 meters per second. By the time they get to the top of that hill, they'll be going 9.5 meters per second. And I believe that that is the hardest question on here. So you've made it through.